Good day, and welcome to Africa Teen Geeks. This is a STEM digital school. If you have just joined into this classroom, this is a grade 12 physical sciences class. Today is the 27th of July 2020, and oh, guys, it's been a long run. We have just finished term 3 last week, Friday, when we were doing work, energy, and power, and we did the Doppler effect. And now we are moving on to the next work, which is our chemical changes. I hope that everybody is ready to do that as we're going to be doing the rate of change, the rate of chemical change, right? So today, it's going to be quite a different lesson. As you guys can see, we're going to be working a lot through the textbook today. Reason being, there's been some challenges with regards to, as you can see, my lesson is kind of disturbed. So, but nonetheless, we will never fail. My name is Nokulego Matondo. I am your teacher for grade 12 physical sciences. So today we're going to be working through the textbook, and I hope that everybody is ready for that. Okay, so we're going to start here. It says that in this module, we're going to be focusing on the relationships and laws that govern chemical reactions. So we will look at the equilibrium in chemical reactions and the factors that can affect these equilibrium. Okay, so we also investigate the redox reactions and that are responsible for the interconversion of chemical and electrical energy in electrochemical reactions. So the rates at which chemical reactants are converted into products vary widely. The combustion of petrol in a car engine is explosively very fast, but rusting of iron is very slow. So it always depends. Each and every element that you have, it's going to have a different rate according to what it reacts to. So for example, like they mentioned them, um, that the combustion of petrol in a car, explosive is fast, but the rusting of iron is very slow. So in certain reactions, virtually all of the reactants are converted to product. But in other reactions, the product breaks up again to reform the original chemicals. But by studying chemical kinetics and equilibria, we can learn how to manipulate reactions to suit our needs. So we revise protons and transfer of acid-base reactions, and one source of electricity is a battery. Redox reactions take place in electrons when electrons are transferred inside the battery. So these electrons can be harnessed to do work, for example, to light the torch of a light bulb. So some chemical reactions are spontaneous and provide energy, while others are non-spontaneous reactions and need to make energy to make them, they need energy for them to happen. So in this module, basically, on this part of module 4 of chemical changes, we're going to be dealing with the rate and extent of chemical of reactions. We're going to deal with the chemical equilibrium. We're going to deal with the acids and bases and electrochemical reactions. Okay. So basically that is what it's all about. We're going to be changing the rate, how long, for example, it takes for reactants to form products, how long it took for the bonds to be broken. So all of those things are all building up to the rate of chemical change. So basically it's got to do with chemical change, but with respect to time. As you know that once you talk about the rate, time is involved. Okay. So I hope that makes sense to you. So I'm just trying to, we can go to a different textbook. Okay. So um, now that you know basically what we're going to be dealing with in this chapter, I want us just to quickly Okay, I think I just moved too fast. Oh no, I think I've moved too fast. Yes, I think this is the part. Yeah, the rate and extent of chemical reaction. But the word already tells us rate. It talks about the time it takes, and the extent is how far the chemicals can fuse together to form a reaction. Okay. In our reaction, we know it's the reaction between it's the reactants together, joining together to form our product. So that is what we talk about when we talk about a rate of chemical equations or reaction. Okay. But I think I've just moved too fast, and here we are. Okay. So um, let's go back and show some examples. So they say in a chemical reaction, the substances that are undergoing the reaction are called the reactants. So if we've got A plus B gives you AB, our A plus B is our reactant. So the substances that undergo a reaction, while the substances that form as a result of a reaction, those ones we know them as the product. Okay, so it's basically reaction and result. Okay, so the reactants they gonna react together to form a product. So the reaction rate describes how quickly or slowly the reaction takes place. So how do we know whether a reaction is slow or fast? One way of knowing is to look either at how quickly the reactants are used during the reaction or how quickly the products are formed. So you can look at one of the two. You can either focus your observation on the reactions because as they react together, there is some chemistry that is happening between them. Or you can look at how fast the product is forming during after the chemical reaction. Okay. So, for example, we've got iron. Here's our iron here, and we've got sulfur, and they give us iron sulfide, right? So in this reaction, we can observe the speed of the reaction by measuring how long it takes before no iron or sulfur is left in the reaction vessel. Okay? In other words, the reactants have been used. So for the reactants to be used, you can calculate how long it took. Basically, from when you put them in together, you can check the time at how long it takes for that to happen. Or you can focus on the product part of it as once the things are formed together, how long does it take for them to form a product? Okay. So in other words, the reactants have been used. Alternatively, one could see how quickly the iron sulfide is formed. Since iron sulfide looks very different from either of its reactants, this is easy to do. So we've got many examples that can show you the rate of reaction, especially with solid solutions. It's much quicker. For example, there's also the one of magnesium and oxygen that form magnesium oxide. In this case, the reaction rate depends on the speed at which the reactant, which is the oxygen gas and solid magnesium, are used. Okay, so or the speed at which the product is formed. So that is all about the rate of reaction, and that is how it is explained. Okay, so we're coming back here. It says here Um, in chemical kinetics, we study the speed, right? We've already mentioned that, and we associate word with kinetic or movement. Here, the change is the rate of the reaction, which is the change in concentration of the reactants or the product this time. Okay, so we're trying to calculate how long it takes for the reaction to take place and or how long it takes for the product to form. So these are basically one in the same definition. So okay, chemical engineers in industry and industrial chemists have to understand the factors affecting the rate of reaction and use them to make more products in a shorter time. Okay, what does that mean, guys? It means that it's very important for them to understand, for example, if you're going to be using iron and sulfur together, what is it that is stopping these two or making them take too long to form bonds? So chemists need to know that so that they can be able to make faster reactions and eliminate the whatever it is that is making the reaction take time to do, because they work with money and they're working with time. So the faster they can make their product or they can speed up their chemical reactions, the faster they can get products and the faster their product can be sent out into the market. So that's basically what that means. So bond energy is the amount of energy required to break particular bonds. So now I'm taking you guys back to some grade 11 revision, an important term that you guys need to know. So bond energy is the amount of energy required to break a particular bond in a molecule. Okay, so we've got two types of reactions that we know that we've been working with since grade 11. It's the exothermic reaction and the endothermic reaction. So what is an exothermic reaction? Is a reaction which energy is released to the environment in the form of heat and light. The temperature of the reaction mixture increases. Basically, an example of this is an explosion where you actually literally see the fire happening, and which is the product part of it. Okay, so an endothermic reaction is a reaction in which energy must be added continually in order for the reaction to occur. So it takes in a lot of energy and for it to form its product. So the temperature of the reaction mixture decreases. So the minimum amount of energy needed for the reaction to begin is called activation energy. Remember that as well from grade 11, we did it a lot in grade 11. It's called activation energy because it's the minimum amount of energy required to break the bonds. Remember, we've got bonds between our reactions. So we need activation energy for us to break the bonds of the reactions. For example, if you have AB plus BC gives you AC plus BD, then you need to break AB and you need to break BCD, right? You need to break those bonds for them to form new bonds with each other. So the only way to do that is by having our activation energy. Okay. So the heat of the reaction or the enthalpy change is negative for endothermic reaction and positive for exothermic reaction. Okay. So now we're moving on to the rate of the reaction. The rate of the reaction or speed of the reaction for reactions or products in a particular reaction is defined as how fast or slow the concentration of the reactant or products changes. Okay. So we want to know basically when you do a reaction, how quick does it break bonds and form new bonds to form new products. Okay. So as it reacts together, the reactants are reacting, but a product is forming. So those two terms mean the same thing. Okay. So the definition is only valid for a single reaction in a closed system of constant volume. For example, if salt water is boiled in an open pot, the concentration of solution increases as water evaporates, but no reaction takes place. A reaction can be represented by reactants and R, which gives you the product, which is written P. So the arrow implies that during the reaction, reactants are used up and the products are formed. Okay, so this arrow here, this is where we have our triangle, or we have our activation energy taking place. And after the arrow, we know that now we've got a product that is formed. We follow the progress of reactants by measuring the decrease in concentration of reactants or the increase of concentration of product. So you can choose whether what you're observing is the rate of reaction between the reactants, or you can decide that no, this is me observing how fast the product is forming, not how the reactants are, the reaction is taking place. So either one of them, but at the end of the day, it gives you one solution. So we can follow the progress of reactions by measuring the decreasing in concentration of the reactants or increasing in the concentration of the product. By measuring the change in concentration, we can determine the rate of the reaction. And how do we do that? We're going to say the rate of reaction is equal to change in reactant concentration divided by time, or we can say the change in product concentration divided by time. So you see, the one on top is change in reactants, and the other one is change in product. So some reactants, such as combustion of petrol in a car engine and the colorful display of fireworks, are explosively fast. Other reactions, such as iron rusting on a rock or weathering, are extremely slow. So reactions don't take place at the same rates. That's another thing we need to know. So reactions also proceed at different speeds when conditions change. Okay. For example, glucose burns rapidly in air, but when used as an energy source in our bodies, it is oxidized at a much slower rate. So one compound or one substance can have different speed of reaction according to what they are reacting with. Okay. So with that one, it burns fast in the air, but when it's in your body, it burns much slower because the conditions are different between air and inside your human body. Okay. So a coal-fired power station uses powdered coal that will combust immediately to provide the heat to change water into steam. But when it's used as a charcoal fire to brine meat, it's much better to use the larger pieces of coal that burn more slowly. So you see, it's one substance, but it works in different rates and in different ways according to the conditions that you're using them for, and not just conditions, but the amount also. It also counts as how you use your substance. Are you using a powdered substance or are you using a large chunk of substance for the reaction? So that also plays a role in this case. So by knowing which condition change the reaction rate, chemists and engineers can control many chemical reactions. As you can see, like as we spoke about the coal, they figured out that when you use coal as a powdered substance, it will burn faster, and by that time we need electricity much quicker. We cannot afford to have a slow combustion reaction. So that's why they powder the coal. But when you want to burn to make fry, your meat needs to be ripe in a specific rate or time. So that will require you to bring large coal so that they burn much slower. Okay. I hope that it makes sense to you guys. So the rate of reaction can also be represented graphically, which they mentioned that the rate of reaction for reactant to products can be represented as a decrease in reactant molecules this time, or as an increase of product molecules this time. So you see, this is the reactant. This is the reactant slowly reacting together and forming a new substance. Or here, first we have no product, right? But as the reactant reacts with each other, a product is slowly getting formed. Okay. So I hope that all of that makes sense to you guys. And the examples presented. So always make sure that you know your definition of reaction rate. It is the average rate of a reaction. Describes how quickly reactants are used or how quickly products are formed during a chemical reaction. So the average time of a reaction is expressed as the number of moles of reactants used divided by the total time. So this is the example that I showed you guys from the other textbook. So now we're going to have one example. Our example says the following reaction takes place. We've got 4 lithium and oxygen, right? And it gives you lithium oxide. Okay, so after 2 minutes, 4 grams of lithium has been used. Calculate the rate of the reaction. So what do? We always know in all chemistry calculations, the first thing that we do is convert what we have to the number of moles, because that's the standard quantity that we use for chemistry. Okay, so as you can see, step 1, we calculated the number of moles. We take what is used, which in this case it's lithium, right? And we have our molar mass right there. And then step 2, we calculate the time in seconds for the reaction. So here they have said that 2 minutes. So we need to convert it to seconds, which is 120 seconds. So the rate of reaction of lithium used is the number of moles divided by time. And that will give us the rate of the reaction, which is in mole per second. Okay, quite simple example, isn't it? I hope that it made sense. And for that to happen, we're gonna need you guys to test it out. So now we're gonna have an exercise. It's exercise. Let me just see if we have it here. Okay. So now they say think about each of the following reactions. Look at your grade 11 textbook for a reminder. Okay. So we've got corrosion, weathering of rock, photosynthesis, and combustion. So it says now, for each of the reactions above, write a balanced chemical equation for the reaction that takes place. Number B, it says rank this reaction in order from the fastest to the slowest. And number C, it says, how did you decide which reaction was the fastest and which was the slowest? So think of other examples of chemical reactions. How fast or slow is each of these reactions compared to those listed earlier? Okay. So I'm gonna do A with you guys so that you guys can continue with B, C, and D, right? So we've got corrosion. Corrosion is like the rusting of iron. Corrosion is rust, basically. Photosynthesis, you know, it's got to do with plants. Withering of rock is limestone rocks being worn away by water. And then you've got combustion, which is basically burning, propane burning in oxygen. So for each of the reactions, write a balanced chemical equation for the reaction that takes place. So these are our chemical reactions. So we're going to choosing iron as an example of metal that rust. We're going to say iron plus oxygen gives you iron oxide, right? And then you're going to balance out that equation. Then we also have one for photosynthesis, which is carbon dioxide plus water gives you that glucose plus oxygen. Okay. So for weathering of rock, we will use limestone, which is calcium carbonate, as an example, which will be calcium carbonate plus carbon dioxide plus water gives you calcium plus HCO3. And then for our combustion reaction, we'll have carbon plus oxygen gives us carbon dioxide. Okay, so these are all the stuff that I'm going to give you guys for homework. I'd like you guys to go and try it out at home and do number B, C, and D, and we will get through to it tomorrow in class. As we start our class, that will be the first thing that we do. Okay, thank you guys so much for a beautiful class. Hope you have a great day. If you want to talk to me, ndlovu@gmail.com. Thank you guys so much for the class. This was our introduction to chemical change, which is basically the rate of chemical change. Thank you guys so much. My name is Nkulewo Matondo. I am your grade 12 physical sciences teacher. And thank you and goodbye. Do not forget to do your homework. Thank you.